In this video, I'm going to try to persuade you that the Euclidean geometry on which we're concentrating is only one out of 9 possible plane geometries, all of which, from the point of view of pure mathematics, are equally reasonable. This is an idea from the 19th century, put forward by Arthur Cayley, a great mathematician from England, and Cayley-Klein, an equally great mathematician from Germany. We will, in fact, in this course, be considering not only Euclidean geometry, but 3 of the other Cayley-Klein plane geometries. And what I want to do today is just put this into a general context. So geometries have points and lines, and plane geometries have only points and lines. There's only one plane. What does Euclid say about points? They have no extent. But another characteristic of points is that if you have 2 points, A and B, there's a distance between these points, and you can move the line segment joining A and B around, and whether you translate it or rotate it or reflect it in something, the distance between the points A and B stays the same. Geometries also have lines. Euclid says they have length but no breadth. And according to that definition, say, a circular arc would qualify as a line, and indeed it does, according to Euclid, but he focuses his attention immediately only on straight lines. And in other non-Euclidean geometries, the only lines we'll consider are the ones that are the straight line in that geometry, though they may not look straight to you when you first meet them. What property does distance have to have? Well, suppose you have, moving from west to east on a straight line, points A, B, and C. And let's imagine that point C is in the middle between A and B. So A is far west, C is in the middle, B is far east. In that case, the total distance from A to B must be the sum of the distance from A to C and the distance from C to B. Now, in any geometry, 2 points A and B that can lie together on a straight line determine a unique straight line, and one way of testing whether a point lies on this unique straight line is that it has to consist of points that pass the distance test above. That is, you can say if 2 cities A and B are 50 miles apart, any city on the straight line between them must have the property that its distance from A plus its distance from B is precisely 50. And I think this is what Euclid means when he says that the points on a line lie equally with itself. Equivalently, that's what we mean when we say that the line is the shortest distance between 2 points. A line is infinite in extent. The English phrase for a bounded line is a line segment. It's bounded by 2 points, one at each end. If a line is bounded at one end only, but extends infinitely far in the other direction, we call it a ray. And an angle is therefore a geometrical figure formed by 2 rays, let's call them little a and little b, that have a common endpoint. And once we've got those 2 rays, there is a numerical value that we can attach to the angle, a so-called angle measure. Sometimes we measure this in degrees, sometimes we measure it in radians. And if we move the rays around, this angle measure stays the same. There's a rule for angles that's like the rule for lengths. Imagine that you have 2 lines emanating from a common point, and then a third line, we'll call it little c, that heads off from the point in between the other two lines. In that case, the angle between A and C plus the angle between B and C has to equal the angle between A and B. And usually this is achieved by using some area as the criterion for angle measure. Now, if we have two lines, A and B, they may or may not intersect. If they do intersect, they'll determine a unique intersection point, or in one special case, spherical geometry, a unique pair of such points. But in many geometries, there are pairs of lines that don't intersect. Lines that don't intersect in Euclidean geometry, as you know, are called parallel. In hyperbolic geometry, we will find that it's frequently the case that two lines fail to meet, and such lines are called ultraparallel. Now let me introduce a geometry where the points and lines are not what you ordinarily think of as points and lines. We start with a three-dimensional real vector space, R3. This consists of points that have an x-coordinate, a y-coordinate, and a z-coordinate. And I'm just going to decree that a point of this projective geometry, I'll call it a p-point, is a one-dimensional subspace of R3, the set of all possible multiples of a certain vector. This corresponds geometrically to a line through the origin. And if you want to try to visualize this, think of a ball of wool and a knitting needle that passes through the center of that ball of wool. That's a point of our geometry. A line of this geometry is a two-dimensional subspace of R3. You pick two independent vectors and consider all the linear combinations of those vectors. Geometrically, this corresponds to a plane through the origin. And now, what you're familiar with is the relationship between points and lines holds in this geometry. Because if we take two p-points in this geometry, two lines through the origin, think of two knitting needles sticking through the center of this ball of wool, there's a unique plane through the origin that includes those two lines. So just as in Euclidean geometry, in this geometry, two distinct points always determine a unique line. What about lines? Well, the lines of this geometry are planes through the origin. If you visualize two planes cutting through the Earth, say, the equatorial plane for one and some plane tilted relative to the equator for the other, you can visualize that those two planes meet in a single line, but that line is a point in our geometry. So in this projective geometry, not only do two distinct points determine a unique line, two distinct lines determine a unique point. But I can do this differently. Again, I start with a three-dimensional real vector space, and now I'm going to introduce the concept of an L point. An L point is a two-dimensional subspace, a plane through the origin. Hey, you say, I thought that was a line. Well, I'm going to call it a point instead. And then I'm going to say a line in this projective geometry is a one-dimensional subspace. Geometrically, a line through the origin. Okay. Suppose we have two distinct L points, two distinct planes through the origin. They determine a unique line through the origin, so two distinct L points determine a unique L line, and two distinct L lines, two lines through the origin, determine a unique L point, the plane that contains both those lines. Now this geometry has a funny feature. Suppose you found a translation of Euclid's Elements in some very obscure language for which you didn't have a dictionary, and you were trying to figure out which word meant point and which word meant line. You could figure that out if you deciphered the mathematics, because two distinct points in Euclidean geometry always determine a line, whereas two lines do not necessarily determine a point. They might be parallel. But in this projective geometry, you can't tell which are the points and which are the lines. This is an example of a so-called self-dual geometry, where you can interchange the concept of point and line, and the geometry remains equally valid. A problem with this projective geometry is it doesn't have a distance function and it doesn't have an angle measure function. So we're not going to go into projective geometry in any more detail in this course. I merely want to point out that it's not always obvious from the mathematical description of a geometry which are the points and which are the lines. Now I'm going to show you three different ways of measuring lengths and three different ways of measuring angle. The names that are applied to these by Cayley and Klein are elliptic, parabolic, and hyperbolic, and I will stick with those, but the question we have to ask has nothing specifically to do with conic sections. Here's the first question you want to ask about a plane geometry. Suppose you have a line of the geometry, this line L, and a point P that's not on the line. Now there are three distinct possibilities. The first one is that any point, without exception, on the line L can be joined to point P by a line. And that's the case in Euclidean geometry. But it may be that there's one and only one point, Q, on line L that can't be joined to point P, and that in fact is the case in so-called Galilean geometry, the geometry of uniform motion along a straight line. In this geometry, a point is really an event in space-time. It has a time at which it happened, and it has a location at which it happened, and a line of this geometry represents motion with some constant velocity. Given two events that happen at different times, you can always figure out a uniform motion that's on hand for both events. But if those events happen simultaneously, you'd have to travel infinitely fast to be on hand for both. That's not a line of the geometry. So that's an example of so-called parabolic angle measure. Finally, there are situations where many points on the line L cannot be joined to point P, and we're going to meet a geometry where that is true, the so-called Minkowskian geometry, which underlies Einstein's special theory of relativity. In that geometry also, the points of the geometry are events with a space coordinate and a time coordinate, but now the rule is 186,000 miles per second. It's not just a good idea, it's the law. Nothing can travel faster than light. So lines joining points that are widely separated in space and close together in time are not lines of this geometry, and in fact we have a whole segment shown in green here on line L of points that can't join with P. In that case, the angle measure is called hyperbolic, and when we study Minkowskian geometry, you'll discover that we take hyperbolic sines and hyperbolic cosines of our angles. Now what about length measure? To figure out the type of length measure, we ask the question, how many lines through the point P fail to intersect L? You say, I know the answer to that. The answer is there's only one line through P that doesn't intersect L. That's the parallel line. And that's true in Euclidean geometry, so we will say that Euclidean geometry uses parabolic length measure. On the other hand, if you do spherical geometry, where the straight lines, shortest distance between 2 points, are great circles on the surface of the sphere, 2 great circles always intersect, so that geometry uses elliptic length measure. And when you study hyperbolic geometry, you will learn that there are in general many lines through this point P that fail to intersect L, and that means in that geometry we need hyperbolic length measure, and indeed hyperbolic distances will be defined in terms of the hyperbolic functions you recently learned about. So we've got 9 different plane geometries. Why? Because for a plane geometry we need a set of points, we need a set of lines, we need a style of length measure, elliptic, parabolic, or hyperbolic, and we need a style of angle measure, elliptic, parabolic, or hyperbolic. To be complete, we should also specify the so-called isometry group, a group of transformations that preserves length measure and angle measure, but we're not going to get into this subject in sufficient detail in this course to worry about isometry groups. Still, we can see with 3 styles of length measure and 3 styles of angle measure, there are 9 possible combinations. And from the point of view of pure abstract mathematics, all 9 of these plane geometries are equally valid. How does Euclid single one of them out? Well, he says 2 points, as long as they're distinct, always determine a line. That's his first postulate, and that tells us that Euclidean geometry uses elliptic angle measure. In the 5th postulate, Euclid in essence says, given a line and a point not on that line, there's a unique line parallel to the given line that fails to intersect that first line. And that means he's using parabolic length measure. However, Euclid scrupulously never uses the 5th postulate until he needs to. That's after proposition 26. So the start of Euclid's Elements applies to 3 of the 9 geometries. It applies to all the geometries that use a style of length measure that doesn't depend on the existence of parallel lines. Here's a table showing the 9 geometries. Going across, we have the style of length measure, elliptic, parabolic, or hyperbolic, and that is determined by the existence of parallel lines. No parallel lines means elliptic, unique parallel line means parabolic, and many lines that fail to intersect means hyperbolic length measure. For the angle measure, we need to know about parallel points. Just as 2 lines are said to be parallel if they don't intersect, 2 points can be said to be parallel or ultraparallel if there is no line of the geometry joining them. If there are no parallel points, we're using elliptic angle measure. If there are unique parallel points, we are using parabolic angle measure. And if there are many points, as in Minkowskian geometry, that fail to join up with a given point, then we have hyperbolic angle measure. So here are the names assigned to the geometry. The most familiar one, Euclidean, uses elliptic angle measure, and parabolic length measure. If we switch the style of length measure to hyperbolic, we end up with a geometry which is called hyperbolic geometry, or sloppily, it's frequently just called non-Euclidean geometry, though as you can see there are many different non-Euclidean geometries. If, on the other hand, we eliminate parallel lines completely, then we have elliptic geometry, and elliptic geometry is almost but not quite the same as spherical geometry. Since spherical geometry is much easier to visualize, we will concentrate on that. Then we can look at other geometries that use the same parabolic length measure as Euclidean geometry. The one we'll study in some detail is Minkowskian geometry. I will mention only briefly Galilean geometry, in which there are unique parallel points. Then there are three other geometries I haven't mentioned, which are Minkowskian, Euclidean, or hyperbolic, with the role of points and lines reversed. If you understand hyperbolic geometry, you also understand cohyperbolic geometry and so on. So we will say nothing more about these three. Finally, there's doubly hyperbolic geometry, which is so weird I'm just going to ignore it. Now, given a geometry, there may be many models for it. A model, you'll recall, is a set of objects. Could be physical, could be algebraic, could be geometric, or could be computational, that have the required properties that satisfy the axioms of the geometry. And I showed you as an example projective geometry, where the so-called points and lines of geometry are really algebraic. They're defined as subspaces of a vector space. When we have a model, what do we have to specify? Well, we have to say what objects in the model correspond to the so-called points of the geometry, what objects correspond to the lines of the geometry, though a line should always be a set of points, how to construct the line on which 2 points lie when it can be done, and how to find the point, if any exists, where the 2 lines intersect. And once we know that, we've got enough information to figure out which of the 9 geometries we're dealing with, and we can figure out what style of length measure and what style of angle measure is used in the geometry. In general, if you have elliptic angle measure or elliptic length measure, that will be defined in terms of inverse trigonometric functions. We'll be using the arc cosine function to measure angles in Euclidean geometry. Hyperbolic angle length or measure will be defined in terms of inverse hyperbolic functions. You'll meet these for length in hyperbolic geometry. And if we have a parabolic angle or length measure, we have the parabolic length measure in Euclidean geometry, that will be defined without the use of either trigonometric or hyperbolic functions. You will discover, for the example of hyperbolic geometry, that there can be multiple models for a single geometry. You'll meet 3 different models for hyperbolic geometry. In one of them, the points of the geometry are points inside the unit circle. In another one, the points are points in the upper half of the xy plane. And in the third of these, the points are points on a hyperboloid. These are 3 different models for the same geometry, and remarkably, the first 26 propositions of Book 1 of Euclid's Elements apply to all of them. If we wanted to do this in substantially more detail, which I do when I teach the classical geometry course during the academic year at Harvard, I'd need to specify for each geometry, given 2 points, how to determine the distance between them, given 2 rays, how to determine the angle between them, and most complicated, what sort of transformations preserve distances and angles. In Euclidean geometry, we have rotations, reflections, and translations, but this gets quite complicated in other geometries. We will be able to compute numerical measures of lengths and angles by using our R software, but doing a complete treatment of the isometry group, which was Klein's great contribution to geometry, is beyond the scope of this course. So I hope this will serve to put the non-Euclidean geometries that you'll be meeting later in the course into a more general context.